Hello, everyone, and thank you for joining me at the virtual EGU 2020. I hope that everyone is safe and well. Despite the cancellation of the physical conference, I decided to still present a shortened version of my presentation, now entitled Hydrothermal Seawater Basalt Exchange Reactions as Traced by Triple Oxygen Isotope Values of Submarine Vent Fluids. First, I would like to start with showing the delta TNO profiles through ultra oceanic crust as measured in ophiolite sections, as well as in modern oceanic crust. So we see the majority of the delta TNO values are below that of unaltered precursor, which is mid-ocean ridge basalt with a delta TNO of 5.5 per mil. That equates to the proportional change in the seawater value. Upon reaction with basalt, it emanates at hydrothermal vent fluids with the delta TNO value higher than that of its precursor, pristine seawater with the delta TNO of 0 per mil. And because each year about 3 square kilometers of ocean floor is being produced, that equates to a rather large amount of exchanged oxygen, providing the dominant control on the oxygen isotope budget of seawater. Now, due to the advances in the field of triple oxygen isotope geochemistry, we can consider the isotope budget of seawater in two-dimensional space. The delta TNO value here is shown on x-axis, and the 17O excess or capital 17O value is plotted on the y-axis. In this talk, I will use the reference line with the slope of 0.5305. And these vectors show the isotope effect produced by each process that contributes into the isotope budget of seawater. And these are the dominant processes such as continental submarine weathering and the hydrothermal alteration. Mind you, the hydrothermal alteration produces more than a half of total fluxes of exchanged oxygen into the terrestrial hydrosphere. It is important to understand what is the isotope effect produced by this process. And one minor detail is that, of course, we can use the delta TNO and 17O values measured directly in altered oceanic crust. However, those measurements are subject to the temperature-dependent fractionation of the exact minerals that were sampled for the oxygen isotope analysis. So in this talk, I am specifically aiming to provide you with the analysis of directly measured vent fluids. So for this study, we used samples collected by a remote operated vehicle in 2017 from the vents of Axial Seamount volcano. It's a volcanic edifice located on the spreading ridge between the Juan de Fuca plate and the Pacific plate of the coast of western United States. The samples were collected from the vent locations where the temperatures were ranging between 200 and 350 degrees Celsius. So now I will show you the magnesium concentrations plotted against triple oxygen isotope composition. And I apologize for reversing the axis here. However, that has been taken from the previous study showing that the delta TNO values measured previously and in these studies are comparable. So the idea here is that you can use the magnesium concentration expressed in millimole per kilogram, so molality, to reconstruct the end member values. Inevitably, when you sample vent fluids, some amount of seawater is being entrained during the sampling procedure. So to reconstruct the delta TNO value of the fluid end member, we extrapolate the magnesium concentrations down to the concentration of 0. And the concentration of 52 millimole per kilogram corresponds to the oxygen isotope value of ambient seawater. And this systematics works because upon interaction with basalt, when you produce a whole bunch of magnesium-rich phases, such as brucite or chlorite, the magnesium concentration of the vent fluid becomes extremely low. So at the first glance, we can appreciate this regression line. It indicates that the end member fluid value, the vent fluid value, has a delta TNO value of around 1 per mil. And the capital 17O would be around -0.1, -0.2. However, if it's normalized to the initial seawater composition, that shift could be expressed, as in 20 ppm change in capital 17O with every 1 per mil change in delta 18O. Next, we would like to show how the chemical composition of vent fluids would change along with their triple oxygen isotope values. To do that, we constructed mineral aqueous equilibrium calculation, in which small amount of basalt is being incrementally titrated into 1 liter of seawater at conditions similar to submarine hydrothermal systems, 350 degrees Celsius and 500 bars. The progress of titration is shown here as mass water oak ratio. All the way to the right, where the water oak ratios are high, the chemical composition of the fluid is being dominated by that of pristine seawater, and all the way to the left, it is buffered by the equilibrium with basalt. So first thing to see, the magnesium concentration drops dramatically at the water oak ratio below 100. However, there's still no change in the triple oxygen isotope value of the fluid. The measurable change in the triple oxygen isotope ratio occurs at the water oak ratio below about 10. And in fact, the water oak ratio of 1 corresponds to the values measured in end member composition at the axial seamount. In conclusion of this talk, I'd like to show the plot where we compare the triple oxygen isotope values of the fluids to the values measured in epidotes extracted from altered oceanic crust and published previously. These are the works where you can find the values for the epidotes. The axial seamount fluids are color-coded here by the magnesium content. The mineralogical control enables us to monitor the progress of seawater basalt reaction with the epidote data. And it is because the triple oxygen isotope fractionation between the fluid and the mineral is supposed to be minimal. The delta 18O values would fractionate within plus or minus 1.5 per mil, while the 17O values of epidote and fluids would be within the analytical uncertainty due to the high temperature stability of the mineral. To remind you, the epidote stability field starts with temperatures of about 250 degrees Celsius. Complementary to this trajectory, the alteration of oceanic crust is shown with a line emanating from mid-ocean ridge basalt. This offset is defined by the fractionation between H2O and bulk secondary minerals. The slope of this line is the same by the sign, but the sign of the change in 17O and in 18O is opposite. Thus, in this talk, I gave an overview of the triple oxygen isotope exchange produced by seawater basalt reactions. We showed that for every 1 per mil change in 18O, the corresponding shift in 17O is about -20 ppm. We show that for the bulk altered oceanic crust, this trend would have the same slope, but with a different sign in order to complement the oxygen isotope mass balance. This approach, the comparison of fluids and epidotes, can be applied to ancient hydrothermal systems with the purpose of reconstructing the values of vent fluids and thus the hydrothermal input into the ancient hydrosphere. That's all I have. Thank you for the attention. Please send me questions to my email and I will try to be present in the chat during the session. However, it turns out that I might have to go to the lab for the first time since the lockdown.